right, welcome back. We're now at week 3. This is a more involved week mathematically. We're going to talk about the physics of light interacting with matter, and as such, I've whipped out the big guns. I've got colored markers finally, and my Maxwell mug. So let's do this. Okay, so in the first couple weeks of the course, we looked at light propagating through free space. We found that Maxwell's equations predict that when we wiggle charges, they emit radiation, and that radiation is light, electromagnetic radiation. We can think of that in terms of these plane waves that move across. And just by doing a bit of math, we got a ton of interesting properties, that light is transverse, that the oscillations are perpendicular to the direction of travel. And the oscillations are consisting of an in-phase electric and magnetic field. These fields carry energy through space, and we can think of them in certain circumstances in terms of rays. And sometimes it's more correct even to think of them in terms of photons. But for the majority of the course, we're going to be treating light as electromagnetic radiation, and we're going to come to the more interesting part, in a sense, of what happens when light interacts with matter. All right, and a very beautiful picture is going to emerge, and we're going to understand this qualitatively very well. And then we'll do a bit of quantitative work, because it can be a bit involved. But we'll go slowly through the whole process and understand how it is that light has an interaction with matter. And that might seem interesting at first. So the electric field is something that permeates all of space. So what does it care if there's an atom here or not? And we know somehow there is some interaction, because if I have a charge and I put an electric field through it, we know from electromagnetism that charge accelerates. So light affects matter. And an accelerating charge, as we'll see, emits radiation. So there is an interplay here. Okay, so let's start with that. Okay, so what does light care about matter? All right, and the key here is, for what we're interested in, is the phenomenon of dipoles. All right, what is a dipole? If I have a single charge, I have a charge sitting here, and it emits, say it's a positive charge. You may have seen before that we can think of it as having lines of electric field which move out, right? So constant electric field anywhere in a sphere around it. Something even more interesting happens, I think, when you have a positive and a negative charge, which are right next to each other. You get what forms called a dipole. So some atoms, or rather molecules, have permanent dipole moments themselves. They have a positive and a negative charge. An example is water. All right, we have an H2O molecule, and due to the electronegativity of the atoms in that bond, something we will not go into, which you'll be happy to hear about, and I'm happy to say because I know next to nothing about chemistry, but just very, very, very broadly, because of the way this molecule is formed, we get a permanent dipole moment. There's a slightly more negative charge on the top and positive charge on the bottom. And the field lines are what we'd expect from a dipole, not radially pointing out, but this other pattern where it kind of loops in. It's in the bottom, out the top, and loops around at the side. Okay, but and this is important, because if we apply an electric field, it will tend, the net charge is 0, but so it's not going to accelerate, but it will tend to align and kind of wiggle its way to align to the electric field, and this is key. But we can't just talk about polar molecules. Everything affects light, right? So even something very simple like a hydrogen, lithium, rubidium, and alkali atom, it's just basically a giant sphere. It's a symmetric sphere. Even that can have a dipole moment, and that has to do with the induced dipole moment. And effectively, it's just that we can think about an atom like a negatively charged shell with some positive core, and if we apply an electric field this way, the positive core will move up along with it, the negative charge will move down, and we're going to have a net slightly more. If we draw a line here, we're going to have slightly more charge above than below, and then we're going to have our dipole moment. This is called an induced dipole moment. And that's kind of drawn here where the colors are representing the charge. Okay, so that's fairly interesting. What I'm interested in, or I'm really interested for this course, is that we snap off the electric field. We turn it off all of a sudden, and then you have this imbalance, right? And opposite charges attract, so it's going to restore itself to equilibrium and kind of wiggle its way back. I have a wiggling charge, that's an accelerating charge, that's going to emit kind of a sinusoidal radiation pattern, right? So that's actually going to be a source of radiation. So that's a wiggling dipole is an emitter of electromagnetic radiation. And here's a picture of what that field looks like. It turns out if you get very, very, very close, the solution, if you actually do the math, is very messy. It's fields everywhere. But as soon as you get somewhat far away from from this dipole, there's a bunch of fields which die out very quickly. It's 1 over r cubed and higher terms. And the only terms that survive in the field is 1 over r terms are these spherical waves which are emitting, right? They're not quite spherical, but if you look at that, there's this spherical wavefront here, and this is the pattern of dipole radiation. And that's why it was so important to understand spherical waves. Now, if you remember, we said this interesting fact about spherical waves. We said that spherical waves could not exist in spherical electromagnetic or transverse waves could not exist in nature because you can't comb a coconut without having a swirl, right? So you can't have a coherently polarized vector that goes around a sphere at all points and is always transverse to the propagation. It's just topologically impossible. So how does nature solve this? It has the spherical-like emitter, and if you'll notice at the top and bottom, along the direction of the oscillating charge, the field goes to 0. There's a 0 crossing. That's where there can be a discontinuity, and we can now have a polarized beam which goes off to 0, then starts off as something else at the top, and there's no vortices, there's no discontinuities or singularities across it, because we have a 0 crossing at the top and the bottom. So if you pictured rotating this in all space, that's what the emitter would look like. And this is what a single dipole looks like. All right? So let's think about what is causing this, right? I mean, there could be a little microscopic hand that's wiggling that force up and down. That'd be kind of interesting. That would be an interesting physical theory. But it's probably a field that's pushing it around. And what field do we know that's oscillating sinusoidally? That's what light is, right? That's what we've been studying light to be. So let's look at that. Here's a light, which is an electric field, which is pointing up and down. And periodically, it's going to be inducing this dipole moment. The dipole, the atom is going to be moving up and down and up and down and oscillating, right? And as we just saw, if that dipole is doing that, then it is becoming itself a source of secondary radiation, all right? So this is the whole picture. Light is traveling through this, through an atom, say. There's probably a ton of atoms around here, but let's just concentrate on one. And the electric field of that is wiggling that dipole with some amplitude, and that wiggling is producing a secondary source of radiation. And what's actually coming out then is the original field plus the field induced by the atom. This is optics. This is all of optics right here. This is it's a very, very qualitative picture, but light induces charges to move, which induces more light. We can think of that in terms of diffraction, scattering, focusing. All the optical phenomena are just like this. So this is a great picture, and this is something I want you to keep in mind. I mean, just take this away from the course, please. This is really a picture of what's going on when light is going through glass or even getting absorbed by the wall here. But we can be a bit more quantitative, and we're going to do the most physicsy thing we could possibly do. We're going to make a quantitative model where we're going to assume that an atom is a mass on a spring. All right, this is like a spherical cow thing, but I argue this is somewhat reasonable at least. Okay, because what is that electric field doing? It's driving that dipole up and down. And if you just let it go, if you turned off the field, it would settle down, right? It would just start oscillating. That oscillation is releasing energy, so it's not going to oscillate forever. It's going to damp out. So this is like a damped, driven harmonic oscillator. The harmonic force is due to the Coulomb force from these separated charges. The driving is the electric field, and the damping is the energy lost to radiation. And this is called the Lorentz Model. So let's just write down the classical mechanics, Newton's equations for this system here. So we have Newton's law, F equals ma. We also have the driving force. This is from Coulomb that says the force on the charge is equal to the charge times the electric field, QE. Great. We also have damping, right? We're just going to call that term gamma. Gamma is the damping rate. We have to times it by m to make things dimensionally correct here. And finally, we have Hooke's law, right? The restoring force, whatever it is. F equals kx. And this is from, if you remember that simple harmonic oscillator theory from first and second year, if you have this, we have a mass on a spring, and it has a spring constant k, and we wiggle it, it's going to move at some characteristic frequency. Omega is equal to the square root of k divided by m, or k is equal to m omega squared. That's where that term comes from. So this is the entire equation that we have to solve here. Okay, so I've just divided everything by the mass, and this is what I get at the end. So let's go about solving it. Now, how are we going to solve a differential equation like this? Well, as you've probably come to realize now, that one way of solving differential equations is you guess the answer, and then you verify that you have the right answer. It's kind of deceptive the way it's taught to you, I think. Really what this is you're asking what physical form it can take. And a nice property of differential equations is if you manage to reason your way and kind of try a trial solution that works, well, that is the solution to the differential equation. So it's being driven at frequency omega, and as it's being driven, the whole system is going to be responding. Now, at the very beginning, there might be some transient stuff that it wiggles this way and that and gets itself settled out. But after it's left on for a few oscillations, the position is going to be responding at frequency omega with some phase, some delay, and some amplitude, right? So we're gonna pick a trial solution. So I'm going to assume that x of t is some x naught. Maybe it's complex, meaning it just has a phase, times e to the I minus I omega t. And if I want to get the dipole moment, that's the part that we care about electrically, we're just going to use the fact that the dipole moment, a little factoid for a charge, is going to be q, whatever that charge is, times x, which in our case is an electron, times x of t. All right, that's the dipole moment. Okay, so let's plug it in. What we have is that the derivative, this is why I love working with complex exponentials this way, is things like differentiation and integration are trivial tasks. You just pull down constants. So this is going to be negative I omega times x of t, right? Times x naught e to the minus I omega t. Let's take the second derivative. All right, so I'm going to get minus I omega again down. So I'm going to get minus I times minus I is negative 1. So it's omega squared times x. All right, that's it. So let's just grind that through the equation. Negative omega squared times x of t minus I omega gamma times x of t, right, from that term, plus omega naught squared times x of t is equal to negative e over mass of the electron, e naught e to the minus I omega t. And then I can pull that x of t out of everything. In fact, that x of t is just e to the I omega naught t. So we can actually completely neglect the oscillation here. It's going to cancel out on both sides, and we can just get at our expression in terms of x and the electric field. And this is what we get. Okay, so let's continue with that. We're just going to solve for x now. We're basically solving for x because that's what we're interested in. So we got omega squared. Just to be clear, omega is the driving frequency. Omega naught is the natural frequency of the system. Minus I omega gamma x naught is equal to minus E big E over the mass of the electron. We'll just divide everything through here. So we're going to get x, our steady state solution. The amplitude of the oscillation is like this, minus E times big E over m naught times 1 over omega naught squared minus I omega gamma. All right, and if we wanted the dipole moment, let's just get the dipole moment. I just multiply this by the charge, minus E, and we have the dipole moment. So that is a nice way of solving an equation by kind of looking at the possible form of the solution. Okay, so here's our Lorentz model. Here's our solution. So we see a few things about it. What we just solved for is the amplitude of that oscillation, and we see that it's frequency dependent. It's going to be biggest, as we might guess, when the driving frequency is close to the natural frequency of the system. And far away, it's going to fall off, and we're just going to get a little bit of wiggling. But near this natural frequency that this atom, whatever that restoring force gives for the atom, we're going to have a lot of interaction, right? So we're going to have a big amplitude of oscillation. It's going to be putting out a lot of radiation, a lot of electromagnetic radiation. Okay, so let's look at the special case first of all with when we're near resonance. Okay, let's look near resonance, where this term, which we call delta, is very, very, very small. So we're going to call delta kind of how much higher we are than the natural frequency. If delta is positive, we're at a faster frequency than the natural frequency. If it's negative, we're at a lower frequency. All right? So in this case, if omega is approximately equal to omega naught, we have this term here, omega naught squared minus omega squared, which is equal to omega naught minus omega times omega naught plus omega, just by factoring. Here we have negative delta. And here we have omega plus omega naught, omega plus omega naught. Since these things are very, very, very close, we can approximate this as 2 times omega naught, right? If this is 1,000 and 1,001, the sum of them is 2,001, which is like 0.05% different than doing the full sum. And we don't want to neglect the difference completely, because that would give us 0 everywhere. So we do want to keep the difference, which is small, but the sum is basically 2 omega. Okay? Okay? Another one of these approximations. So once we do that, we can make this approximation and then factor out a few things, and let's see what we get. When we do that, we just write it up here. Basically, we're pulling out an omega squared. Maybe I'll just do it on the whiteboard here. So we have on this denominator term, we have now negative delta, or rather negative 2 omega naught delta minus I omega naught from this approximation, gamma. So we can pull out that omega naught. In fact, let's just pull out a negative omega naught, which is where we get, which is what we do here. We can pull everything out, and there we have it, the near resonance approximation to the dipole moment. Okay, and we can plot that. We can plot that resonance. Notice it has a real and an imaginary part. The real part, if we plot that, it goes as this, what's called a dispersion curve, and we'll see why a bit later in the course. It goes up and down. And the imaginary part is this, what's called a Lorentzian curve here, aptly named, which is peaked at 0. So notice the dispersion, the real part goes to 0, and the imaginary part is sharply peaked here. And this is going to be important because one of them is going to give us the speed of light in a medium, dispersion, and one of them is going to give us absorption. Okay, so I want to pause for a moment, because what we've done is really half the picture here. We found that when electromagnetic field passes through, the sinusoidal light field passes through atoms, it's going to jiggle them, and that's qualitatively, we argued, going to create its own light field and affect the light in this way. We've also found the amplitude of those oscillations given an electromagnetic field of a given strength. The last part, the second part of this video, I want to talk about relating that dipole stuff we just derived, relating that to the actual optical properties we're familiar with, okay? And this stems from the following. So when we're looking at atoms, we just found what happens to a single atom, but often you don't have a single atom just floating around in space. You have like 10 to the 23, 10 to the 24 atoms for every cubic centimeter or something like that. So we have just a dense bulk sum of atoms, and they're all being driven by the electric field. And the separation between these atoms is on the order of angstrom, less than a nanometer, whereas the wavelengths are hundreds of nanometers. So they just basically see this smooth field, and all their neighbors and themselves are being driven by the same field at the same time. So what we really care about is the bulk properties here. And as light is passing through and they're emitting their own dipole fields, what we're going to get is the original electric field and the field due to the dipoles. We're going to get the sum of the two of them, okay? So in order to derive that, we're going to look at the bulk properties. So we're going to define a terrible word for optics, the polarization field, because it has to do with the polarity of the atoms. Polarization is also a completely separate word, not directly related, that tells us the direction of the wiggling. So careful there. But we're going to look at the macroscopic, the dipole moment per unit volume, and we call that the polarization field. So I'll be careful to call it the polarization field for these lectures, but later in the course, when we say polarization, we just mean the wiggling direction of the electric field. A reasonable thing to assume is that the response is linear. That means if I turn off the field, I get 0. If I put on a small field, I'm going to get some induced polarization. If I double that field, I get twice as much. So linearity is, we're going to assume that the polarization field is proportional to the electric field, which is pretty reasonable. It's not always the case. If we have a very, very strong field, we enter the regime of what are called nonlinear optics. But we're not going to deal with that yet. So we're going to assume linearity, and it has some constant of proportionality. And typically, that's written, we factor out a epsilon naught already, and we call that constant of proportionality epsilon naught times chi, which is the susceptibility. And that is the constant of proportionality times epsilon naught that relates the polarization field to the electric field. We can relate that to the previous result because this is equal to the dipole moment per unit volume. We have an expression for the polarization field in terms of these resonant properties, and we can extract that constant of proportionality out just by staring at that equation. We can find what chi needs to be. So chi, the susceptibility, which is gives the relation between the induced polarization field to the electric field, is related through our Lorentz model through this equation. All right? Okay, that's one. That's part one of relating it to light. The second part is really zeroing in on this field plus this field. And the way that is typically done is the so-called displacement field. Okay? So we separate the two things. We say the displacement is equal to the polarization plus epsilon naught times the electric field. Note that the displacement and the electric field have different units, right? Even the polarization goes to 0, the displacement field is epsilon naught. But this displacement field here captures both the field that's originally applied plus the induced polarization, okay? And since the polarization field is, induced polarization is linear, it's reasonable to assume that the displacement is linear. So it has a constant of proportionality as well, and that constant of proportionality is called epsilon, the permittivity, right? If we go all the way down to vacuum, we have epsilon goes to epsilon naught, and D is just equal to epsilon naught. In general, though, in a medium, epsilon is greater than epsilon naught. And this is the proportionality between the total field and the applied field, right? If the induced polarization is linear, so is this. And we have this constant, this new term, which is epsilon. This is a convenient parameter. You'll see it a lot in data tables and handbooks that they'll quantify the optical properties of matter with this epsilon. They'll just give you epsilon, or sometimes the ratio of epsilon to epsilon naught. So this is the permittivity. And what's nice about this is that we can rewrite Maxwell's equations, those things we remember way from lecture 1, we can rewrite them instead of in terms of the permittivity and the permeability of a medium, right? We had mu naught and epsilon naught before. So we had this in vacuum. It turns out in a medium, this is true. The displacement field is equal to 0. And we have a similar relationship between the rest of them. So this is Maxwell's equations in a dielectric, in an insulator. Why do I say an insulator? We actually have to add a couple more terms if there's free charges that zip around. If we have a conductor that has current which is flowing around, we have to add a few terms to this. But let's just concentrate on plastic or glass or any insulator, which we call a dielectric here. These are Maxwell's equations. These are the exact same equations with different symbols as we had in free space. So now we have our wave equation again, automatically, right? We just call D's E's and epsilons epsilon naughts and so on and so forth. And our Maxwell's equations have the wave equation with a wave, without the naughts, right? So the wave speed is equal to 1 over, remember before in vacuum we had V is what we called C is equal to 1 over epsilon naught mu naught. That was just what came out of the wave equation. And now we have the same form of the equations with V in the medium is equal to epsilon times mu. Okay? So we can quantify this just by looking at the ratio of the two. C over V, which is equal to, if I just do this division, epsilon over epsilon naught times mu over mu naught. Mu is just the bulk permeability of the medium. And for almost all substances we care about in optics, they're not really magnetic. They're not magnetic, and mu is about equal to mu naught. For nearly all material, mu is about equal to mu naught, so we can say that C over V is equal to epsilon over epsilon naught. And there's a name for this, by the way. There's a name for C over V. We call that the index of refraction, for reasons we'll see next video. So we have a relation between the speed of light in a vacuum and the material in terms of these material properties. And often we can just neglect the mu part. So it's like epsilon over epsilon naught, square root of that. Okay, all the dominoes are set up, and now we flick them, and we're going to tie everything together. Let's do what we did before. So we have D is equal to epsilon naught E for a linear medium. And in general, it's just equal to epsilon naught E plus the polarization. And because we're assuming linearity, that's epsilon naught E plus epsilon naught chi times E. That's the polarization, right? So this is equal to epsilon naught 1 plus chi times E. And that's this term here, epsilon E. Epsilon E is equal to epsilon naught times 1 plus chi times E. And we have something times E is equal to something times E, so these somethings are the same. That will give us the nice result that epsilon over epsilon naught, right, which is a much smarter way of writing it than the way I'm about to write it, the square root of epsilon over epsilon naught squared, right? Why do I write it this way? Because this is n squared is equal to, so this left-hand side is equal to 1 plus chi. So the index of refraction of a medium is equal to the square root of 1 plus chi. All right? So that's what we've done here, just to re-summarize. We've used the term that describes the displacement and used linearity, and by comparing the two of them, we get our expression for 1 plus chi in terms of the index of refraction squared. So it's the square root of it. And often it's small too. So we'll often see for small chi, we'll see that we can use that small Taylor expansion, small chi Taylor expansion, 1 plus 1/2 chi. We've done some heavy lifting, and we've arrived at this nice result where we have got the index of refraction in terms of chi, which we got from our model of looking at atoms as simple harmonic oscillators, right? We had a collection of atoms, we're assuming they're all the same, and this is what the index of refraction is for this. And we can plot now the index of refraction. I didn't use any approximations here, I just did the full square root one here. The index of refraction has the real part of it, like this, and the imaginary part as this Lorentzian peak here. And this is what we get. So a typical atom won't just have one resonance, it turns out. It has many levels, so has many kind of normal modes of oscillation. Quantum mechanically, these are just the discrete levels that the electrons can be in. But if you look at the property of matter, there'll just be a bunch of these resonances, and they can interact in a certain way. So this is a plot from just a paper I pulled up where they're actually doing this. They're looking at the index of refraction of a given material for various varying a parameter. We have the real part, which is just these dispersion curves, and they're all accompanied by a Lorentzian dip. There's one thing that might stick out and make you scratch your head if you've done Snell's law before, is complex index of refraction. What does that mean? It says the index of refraction, which is what we plug into Snell's law, right? When we did this stuff before, it's complex. So that's a bit puzzling at first, but it turns out it has a beautiful picture. Wraps everything up. Because you might notice that you can see me. In other words, I'm not perfectly transparent. So therefore, light isn't just refracting through me, it's also being absorbed and re-emitted, right? And that turns out that all we know about lenses and light bending through glass and stuff, that's summarized by the real part of that index of refraction. But the imaginary part is going to tell us exactly how much light is going to become attenuated as it propagates through something. We've done way too much for one video already, I think. So we're going to save that for video 3 of 3 this week. And for now, we're just going to summarize. So the first thing that we did is we looked at a qualitative picture of what happens to induced dipoles as light is jiggling them back and forth. They're going to re-radiate. And all of optics is kind of hidden in that picture. But we went a bit further and defined a quantitative picture of that using the so-called Lorentz model. And we said that what actually is happening to these polarizable atoms as light is going through them? Well, they're going to have some natural frequency if I just let them go. They're going to wiggle at some omega naught. And that the consequence of that is that we can model it as a damp-driven harmonic oscillator and come up with an expression for the magnitude of that dipole moment. Finally, last but not least, we can relate the properties of these induced dipoles to the index of refraction by looking at Maxwell's equations. And what is the index of refraction? It's the ratio of the speed in matter to the speed in vacuum. And that is really determined by these induced fields, these polarization fields. We can think about it that way. So that in doing that, we got an expression in terms of the atomic properties, the resonant frequencies, and how much damping we get. We got an expression for the index of refraction, which turns out is complex. So a lot for this video. This is the Lorentz model where we looked at microscopically what happens to light in terms of individual atoms. Next video, we're going to look at a macroscopic picture. We're just not going to assume anything, any Lorentz models or anything like this. We just have some bulk properties. We have epsilon, we have mu. And look at what happens at an interface. It turns out that by doing a few scribbles on the whiteboard here, we're going to get the law of coplanarness, the plane of incidence, reflection, refraction, and not only that, how much light we expect to bounce back. And that will be next time. So see you then.